All right, so I totally forgot to start recording, so if you're at home or sick or whatever, sorry about that. These are the homeworks for the rest of the chapter. This is tonight. We're planning to, on Friday, have our mastery since today is Tuesday, and we're diving into the 6.2.4 lesson. Savannah, feel better. In my one high school class, if we know that kids are gone, like it's pretty much an expectation that they'll watch the video. So we leave code words hidden in the video. That then, if the person who was sick comes back and they know the code word, I like give them all candy or something.
Can we do that?
Yeah, we could do it for Savannah. I don't know if she's gonna watch the videos or not. She might. What do you want the code word to be?
Banana, since we're all like.
Odd things going on inside your guys' head.
Artificially flavored cough drink.
Yes.
Okay, Micah just got really excited, so artificially flavored cough drops.
Yes.
Savannah, if you come back and you can tell me the code word was artificially flavored cough drops, we'll all have candy.
And so there was
All of them?
My candy's from Halloween. I gotta get rid of it at some point. Well, and I'll probably go at Valentine's Day, like the day after, and buy new stuff, like stuff on sale. Then anything that is branded for a holiday, you should be able to find on sale the day after.
Yeah.
So all the chocolates that are heart shaped. Did you what?
I don't like chocolate.
No, I just.
You don't like chocolate?
All right.
Oh my god.
I got a random card today because I got to make sure I keep talking with everybody. So, reminder, you may skip, but I would encourage you to try the problem first. Remember, we're in a safe space here. So, Caitlin, what do you think when you look at rectangles A and B? Are we similar? Are we congruent? How do we know that? What's your justification? Because I didn't say they had to be one or the other. We're just saying, are they? Wait, now you're changing your mind? So let's have a conversation about this then. What does congruent mean? Same shape, same size. So congruent. What does con mean? Together.
Oh.
So congruent, together, they're the same. So they don't have to be on like the same location, but they're the same. So unless we really get technical, me right here is congruent to me right here. Right? I'm the same person, same size. I'm in a different location. Now, what's it mean to be similar? You gonna help me out or you're gonna move on? Move on. Braylon, what's it mean to be similar versus congruent? Yeah, different how? Yeah, what's that word that means changing the size of a shape but not changing anything else? Anybody?
Dilation.
Dilation, right? To dilate or a dilation. So, when we look at A to B, well, I have a 4x2 rectangle here. And 4x8. What do we think? Okay.
It's been flipped and then dilated by 2.
So we would want to say A is similar to B by a scale factor, and if we know what SF means, we can abbreviate, not San Francisco, right? By a scale factor of 2 or 1/2. It actually depends which way we go. Right, so starting at A, going to B, that's a scale factor of which one? Yeah, 2, right? Because we got bigger. Starting at B, going to A,
It's 1/2.
scale factor 1/2. So if we say that we're going A to B, scale factor of 2.
So if I'm doubling something and or if I'm making something bigger by a whole number and I want to change it back, I would make a line
Reciprocal.
above the number.
Reciprocal. Yep, reciprocal. All right, so now we're going to take this to the next step. how did they get A to B? So there is not, okay, I give up. There's not one right answer here. So if we've determined A is similar to B, or more so B is similar to A, because we're assuming B is the result after, how did we go from A to B? And there's not one right answer, right? There's a lot of ways. So on your paper, list out what translations or transformations will take A to B. And so if we want to rotate or things like that, remember we have to determine where we're rotating from. You could rotate from a corner of the shape, or you could rotate about the origin. Remember, those will do two different things. About the origin is going to change what quadrant it's in. And if we just go around like one of the corners, it just does it right there. I bet you could do this. I guarantee you can do it in 4 steps. I wonder if you could do it in 3.
I can do it in 2. I can actually.
I disagree. I want to see. I might. Yeah, I could be wrong.
Well,
I've not planned this all
the
day.
dilation doesn't actually count.
Yeah, it does. That's a transformation.
Okay, so the
Yeah.
dilation counts.
Dilation 100% counts.
So it expands like this.
So you're dilating from that point. So we also have a center of dilation. So be careful with that.
So and you could from there to there. So you rotate it from there or reflect it from across there.
That's a creative way to do it. I didn't even think about the reflection because we haven't done a lot of that yet.
Or again, you could rotate it from there.
Is there a way that you could rotate and get it to land where you want it to land? And so from that corner won't do it, right? Because if you rotate it up from that corner, it'll be out here. So essentially I'm challenging you, what center of rotation to my enlarged rectangle would take it where I want it to be? And test it. So I'm going to sketch up here an idea that Quinn just had that kind of blew me away. Gosh, my smart board's messed up. I don't know how this happens.
Smart board ain't smart.
Well, I think it's also because mine's mounted to the ceiling and there's some slight vibrations, so the projector kind of moves.
Isn't every smart one mounted to a wall?
No, most are mounted to the wall, like you just said. Mine's mounted to the ceiling, my projector. Every other one is the newer version where the projector's attached. But that wouldn't work here with my TV. So I'm okay having an older smart board. I just have to deal with that nonsense. So Quinn gave me this idea that if we dilate first, my corner actually lines up there. And this is when I love getting proved wrong. Quinn was like, I can do this in 2 steps. And I was like, you sure? He was like, yeah, you're wrong. I like being wrong. How could we reflect from where we are, the blue rectangle, and land on B? Micah?
Like, that way?
If we reflect the diagonal line,
Whoa.
right? Because this will come straight to the reflection line, straight out here. That point on the reflection stays there. The points that are up here come straight to the reflection line, go straight through. And this straight to the reflection line, straight through, if my lines were better. That would do it. Then I challenged Quinn. I bet you can do this with a rotation, but you have to determine the point where that'll actually get you there. Did you figure that out, Quinn?
I think so, but I would think to actually test it well, I would need the simulator.
So what point do you think? What are you hypothesizing?
Maybe -6, or no, 6, -6.
6 negative. So if we go from here,
But I'm not too sure about that.
That won't work.
because actually this will then come here, and my rectangle would be out here.
Well, actually, then to fix that, you need to go to 2, negative 6.
2 negative 6?
2 negative
2 negative 6 is here.
Well, yeah, but I'm not sure.
I'm going to leave this one out there hanging. What?
I have an idea.
Okay.
So, like, if you do this negative 6, even though it does, like, go over there, you can translate it. But we're trying to do it in 2 steps. Oh.
Yeah, that was because I just challenged him. Like, so we could obviously turn it around one of the points, right? Like, we could rotate it around this point, but then my rectangle would be like out here, right? Like off to the left here, and then I could just translate it. I was just challenging for how can we do it in 2 steps. Yeah, that rotation point's kind of challenging. Connor?
How about 5 negative 5?
5 negative 5 here. So like my hockey stick, right and up becomes then, I don't know. I'm gonna let you play with that. We're gonna keep moving on. I want to leave some questions unanswered that leave you curious, right? We don't want to just answer everything. So guarantee there is a point that would work. Problem is just finding that point.
It doesn't have to be an intersection, right?
It doesn't have to be, but a lot of times it will be.
Well, I guess you don't really have to start from that 4x4 area.
So we essentially want this point to come here, this point to go there, this point to go there, and this point to go over there, right? We're going to leave that there.
Yeah, I think I just got it too.
You got to test it for me to believe you. All right, so as we talked about at the beginning of the lesson, congruent together, they're the same size. So we can call that a scale factor of 1, which obviously its reciprocal is just 1. So as Quinn and I were talking about earlier, that obviously proves that we didn't change anything because there's no going backwards. So what transformations keep us congruent? And we can just do this as a conversation. We don't have to like write it down or anything. Or I can just open the question up. What transformations keep it congruent? What don't? Or like you can just tell me what don't. Like what are dangerous? What transformations preserve size? I'm also just taking some time to review because we had so many days off. Yeah, Quinn?
Transformations that keep the size or translation.
Okay, translation is one. Teeth, you got one? Rotation. Keep size. Mallory? We have translation, rotation. What else? That keeps size. Dilation changes size. Careful. What other rigid transformations did we have? Reflection. Are there more? Not that we know of yet, at least, right?
What?
Yes.
Oh, wait, there's more.
There's probably always more. All right, so check out 78. We want to sketch this triangle on our graph. So either make a new 6x6 or use the one you got. And then we're going to follow Angelina's steps to check if we remember how to do each of these translations. Or transformations, sorry. The only difference is since there's a dilation here, that counts as a transformation as opposed to just a translation. Translation just changes location. So translating like to the right or up or down or even rotating kind of counts as a type of translation. And then So Angelina's steps are up on the TV. Once you get Angelina's done, try these. Yeah, if you have a book in front of you, that will make your life easier. So actually, you can still see all of Angelina's. That's her first step. This right here, that's her step 1. So Angelina, V, do 2 different things. Question we're really answering is it different? Are you trying to see the coordinates of the triangle, Brennan, or what? Right. It's so your one corner is at -1, +1.
Oh, okay.
Then -5, +1.
Oh, okay.
-2, +4. Right here, I'll put these steps. Or I'll put all of. Oh, it's broken now.
You broke it.
It just does that random. It just glitches and then won't take the screenshot right. And then the screenshot is like nothing. Sad day.
What is a screenshot? I didn't see.
So you can just capture what the screen is. It literally just takes a picture of everything on the screen.
Well, yeah.
There's your triangle if you still need to see it. So here, I'll do a screen capture to put it up on the TV. So let's go ahead and do Angelina's steps. We reflect the x-axis. Now be careful to remember which axis is the x. It's your horizontal one. Right, so I come down to here, and here, and here. So that's after step 1. And we would call that a prime, because we've done one thing to it. Put 1 apostrophe there. Rotate the triangle about the origin counterclockwise. So that it's always off like the new shape. So where am I going to land? If I do hockey stick method, guys, if you're still struggling with rotation, please give me some attention right now. To get to the origin, I make a path that is a hockey stick. And then I rotate that path. So it's easiest if I make mine go up and right here, because then to rotate it, instead of up right, down right. Because I go 90 degrees. See how that rotates? This is our quote-unquote hockey stick. And it turns it 90 degrees down to here. That's the hockey stick method. So now our new hockey stick for here, 1 up, 5 over, rotate the hockey stick, 5 down, 1 over, right here. Questions? Are we okay? And then up, over, turns it. So my 2 will be here, over. So our new triangle, boom, boom, boom.
That looks the same as reflecting it. It's horizontal.
You might be noticing something. Dilate the figure by a scale factor of 1/2. And if it doesn't tell us a center of dilation, it's the origin. So if I dilate everything by 1/2 from the origin, I got to get rid of some of these hockey sticks. And I got a lot of stuff here. I don't know even how to do this. This point does what? How can it dilate by 1/2 and not change? If you haven't dilated it yet, dilate it. And if you have, follow these steps to do this. I'm worried about what you're doing because this point has to move. So that's what I'm trying to get people at. I think a lot of us dilated it from the corner of the triangle. If it's dilating from the origin, guys, this goes to the halves. Not 1 - 1, but 1/2 - 1/2. Notice how it said multiply each coordinate by 1/2. So if this was 1 - 1, multiplying by 1/2, I get 1/2 - 1/2. Right? This point is 4 - 2. So if I dilate that by 1/2, I end up at 2 - 1. I'm getting awkwardly layered on top of here. 1 - 5, 1/2 - 2.5. Questions on that? When we dilate from the origin, it either stretches away from the origin or comes in tighter to the origin. Now, what would have been easier was the route Caitlin was trying. She said, well, if I just dilate it from this corner, I can just, pull these things back in closer. That would be easier, and then it would be inside instead of awkwardly kind of overlapping. Now, if you want to play tricks on your brain, though, you can kind of get your brain to think this looks three-dimensional. Like, if these were connected and these were connected. But, moving on. Questions on this? One last chance.
I do have questions, but it doesn't.
For the 90 degrees rotation, I got it so it was still in the leftwards.
You did not rotate from the origin. So that's the issue, is it says about the origin, so we have to trace back to the origin and rotate from there. So if you can imagine grabbing the entire shape, like our blue shape right here is what we rotate. You can imagine grabbing that whole thing and just saying turn around the fixed point here. So kind of like that's your pivot point. So like if my foot's triangle A and this is the origin, I rotate.
Yeah, I always kind of imagined like if this is the triangle from the corner, it would just be like this.
Yeah, because you made your center of rotation, that corner. Which you can, but we got told to do it by the origin.
Yeah.
Make sense?
Got it.
Other questions? That was a really good question. Caitlin's just laughing at me up here like dancing. Look, I see you guys. It's really easy to see everything that's happening from up here. Do these steps. Start again with the original A. Follow his steps. V? I'm guessing probably. But VEE could be like a boy's like.
Yeah, it could be like a short name.
Or it could be like Indian or some other culture that just has other names. You're what?
No, usually when I've heard that name before, I always use that as a girl's name.
I mean, I think it could go either. I mean, I've heard my name before used as a girl's name. Micah gets spelled differently. It's in like MYKA. Different spellings like that. Guys, when I look around, I shouldn't see people just staring at me unless you're done with this problem. Because it's awkward. Where am I coughing up? He translates. Ooh. Now the rotation is from a vertex of the triangle. annoyed because my smartboard's like half a unit off. The line x equals 3 is the line made at every point of x equaling 3. Does x go this way or x go this way? X is this way, so go to x equals 3, and then this x equals 3, that x equals 3, x equals 3, x equals 3, x equals... So it's the vertical line at 3 is the line x equals 3. That's your... Now we have to rotate first, right? I've not done my rotation, but I heard people mumbling about that line, the x equals 3, or a y equals line, that it's just telling you the information. So make the line where x is 3. 3, 0, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3. All those points are x equaling 3. So it says rotate 180 degrees about its top vertex point. So I'm going to assume that one. Right, so 180 degrees, I can still do my hockey stick. But now, instead of just turning it 90, I turn it 180, right? So now instead of going left, up, well, I'll continue to go up, actually. So that's 1, 2, 3, 1, 2, 3. Which direction do I go, left or right? Left on this one. It's the opposite. Okay, my smartboard's really making me mad. But this hockey stick, imagine turning it 180 degrees. Right, that L now will be here. Right, are we with me on the hockey stick? 180 degrees, totally spins it up. So that point that was bottom right ends up here, there. Gross. And we can do another hockey stick. Yes, I am. So this is a 3, 3. So now 3, 3, right? Or no, that was 2. Probably gotta go one more. So then here, I know this looks really messy, but our new triangle should look like that. That's after your rotation from that top point. Are we okay? If not, I want to know why.
You wear me out.
Wouldn't, because you guys would translate it first and then rotate it?
Yes.
Wouldn't it be different?
I did do my translation. So my translation landed on blue.
Oh.
So I started at black, went to blue, rotated up to purple, and now the last thing we have to do is a reflection, which I don't really want to do since my smartboard sucks today. So here's the interesting thing. What do you notice about these top points?
They're the same across each line.
Yeah, they're 2 away and 2 away. So when they reflect across this line, your new, quote unquote, new points are each other. You have a new point here and a new point there, but then this point has to move over to here. So our final triangle. Sorry, I know that's like the sloppiest thing ever.
It's a kindergartner's artwork.
So Octavio, if we were to ask you V's end triangle compared to Angelina's end triangle, are they congruent, similar, or neither? Talk with your partner close by you. What do you guys think? Are they congruent, similar, or neither? The end triangles.
They're congruent.
Get kind of sloppy.
No, they're congruent.
I'm gonna just cast some votes. Peyton, what do you think?
I think that it's both.
Both?
Yeah.
George, George isn't here today, is he?
I have no idea.
He might be on a school visit. Olivia, what do you think?
Oh yeah. Oh yeah.
No idea. What does congruent mean again?
That they're the same.
Same size,
That
right?
one's not the same. That one's
No, it's the same.
Did V
No.
dilate his triangle?
No.
Did Angelina?
Yeah.
So could they be congruent?
No.
Oh, they're
I thought you were
similar.
talking about the end result there
End.
between A.
And no, like Angelina's end triangle
Okay, we're comparing them.
and V's end triangle.
you were doing these starting.
Okay, so now that we all understand the question, I just want to make sure we're clear on similar versus non-similar, like congruent versus just similar. Congruent is similar. Okay, I need your eyes real quick. Congruent is similar. It just also has the requirement of same size. Similar keeps the angles all the same, right? When you shrink or expand a shape, the angles don't change, but the lengths do. Okay, so that's the difference between congruent and similar. Congruent shapes are similar. They already checked that box, but then if they're the same size, yeah, I'm gonna fall one of these days, they also are congruent. Sorry, I don't like sitting on normal chairs. I don't know why. Like, I just, even at home, it's weird. All right, I want to see how different we all are. With your team, partner, whoever you're sitting by, you want to take C and get it to land on D. You want to move C. I don't care how many steps, but then we're going to random card and test some of these out. I will give you 3 to 4 minutes to determine your process. How do we get from C to D? My advice is use easy processes. Like if you're going to rotate, I'd maybe just rotate like around one of the corners of the shape instead of around the origin. But you can do whatever you want, really. This could actually be really fun. If I do one person for one step and then a new person for the next step. Let me adjust my zoom. That might be a zoom issue. So I reset it to the original. Yeah, it is between. So even unzoomed, it does not land on the intersections. So that is not a zoom issue. That just is what it is. So C is on intersections. D is not. Let's try this out. This could be really fun. Yes. Quinn! Give me move number 1.
The dilate by half.
From what point? If you want to go from the
top
origin,
left.
top left. No, this is a Quinn step. So Quinn said dilate from top left. George, give me step number 2.
What? What are we doing?
Welcome back.
Welcome back to reality.
We're making D. No, we're making C into D.
Wait, we are?
Yeah.
Wait, what are you
Directions. Figure C to become figure D. If you really wanted, I was just joking, but if you really want to, you can. Gabe, give me the next one. We have red shape now.
Here.
You're fine, man. I know where you live.
I know where you live.
What? But yeah, we have all of your addresses, so if you want to get creepy, I do know where you all are.
I know where you live.
Gabe, there are a lot of options, so don't get yourself stressed out. So you're saying, like, reflect the y, then reflect the x? Yeah. Now, I would agree with you, but that's going to land my shape pointing up.
Oh my.
Like, the fat part would be at the bottom. So we could still rotate then, but I feel like that's a little difficult to make that and I'm already lined up on, like, halfway points. Kind of awkward there. You can do what you're saying. I'm just asking you if you really want to do that, because then we're going to be on top of D, and my drawing's going to get really complicated. I just don't want to draw that, because it's going to get gross. Like, it just, once you start drawing on top of things, give me another option. Chloe. Nope. Nope. Chloe, give me another option. Chloe.
Your name is not Chloe.
Around what point? Yeah! If we rotate around the top left point, that's like the easiest option right here. Because if we if we do a clockwise rotation, so we either have to say 270 or 90, depending on what direction we're going. This stays, that comes down to there. Now I'm pointing the right direction. Now I just need to translate, right? So I just have to determine.
You have to work with halves.
I do have to work with halves. So to get to there, I got to go 1, 2, 3 and a half left. So actually we could say minus 3.5 since we're going left. And then down 1, 2, 3, 4, 5, 6. Crap, I'm not far enough over. That's 4.5. Well, you didn't say, so you should have said. You know what happens when you were about to say? Nothing, because you didn't say. And then down 1, 2, 3, 4, 5, 6.5. And there we are. Now, that's just one way, and literally, you could make infinitely many options here. This is one of those mathematical, like, you could translate it out to 1,000 and then bring it back. You could dilate it and then just bring it back. Now, Quinn, why were you regretting your decision?
Because what I was thinking was you would dilate then rotate, which I realized.
But you did dilate then rotate. How are you going to change your dilation?
I was going to change my dilation to go to the bottom right.
Yeah, you could do that too.
Because then the corners are now on half points.
Yeah, I agree with that. What if we did it from the origin? Just taking us back to the idea of dilating from the origin. This is 6, 5, right? So it becomes 3, 2.5. 2, 5. So 1, 2.5. Or maybe I shrunk that down too far. Or no, that's not 1, that's 2. So there, and there. And we're like out of time, but this does bring us closer to where we want to be. So sometimes dialing from the origin is better. You guys can go ahead and start packing up. 5, 2 becomes 2.5. 1. So that would be if we had dilated from the origin first. Kind of. So we did the comparison of similar versus congruent of. So we first started comparing A to B, how we could get from A to B, the fact that they are not congruent, but they are similar. Then we kind of went on to 78 and looked through like what happens with Angelina's steps, what happens with V's steps to make sure that we like know how to follow those steps accurately. I think I snapped a couple pictures of that. Maybe no, my smartboard started screwing up. So then we talked about how because Angelina dilated and V didn't, their resulting shapes can't be congruent, right? Because one of them changed size. And then we were just playing with this.
Okay.
Yeah, we just took our time today. trying to ease through this stuff a little bit because you guys like had snow days and everything, but like we're planning to take your test Friday is the other important thing.
Okay.
So the planning lumps chapter 6 and 7 together, but chapter 7 totally changes gears, so I'd rather do an assessment over 6 and then move
Okay.
on. Yeah. Thanks, George.
Cool.